This is just going to be a quick video to show people how to um, create and edit creatures in a text file for Keiwan's Evolution. I know a lot of people using the program have been asking about how to do that, and I've spoken with Keiwan through email, and he basically said there wasn't a way, so I made one, in a sense. Now, I can't take all the credit for this because basically all I did is figured out how to manipulate the saved environment files to use them as a saved character file or saved creature file. And so, any rate, I'm going to take a template that I've created, very simple, minimalist template, create a copy of it, and I'm going to rename the copy to 7. Let's just call it 7. And 7.txt is the text file. If anybody wants to find this, again, it might take a little looking on my system. It's in an Evolution saves folder. I've heard there's information out on forums and stuff for the different systems, but you can take a look at what's on my screen if you want and see the path to where it is on mine. And there's the actual template itself. In the copy, of course, 7.txt. Now, if I just run that, let's say I go back to Evolution and I just, clicked in there and created a, well, it doesn't really matter because this is all going to go away anyway. Just load simulation, and that's my template. Okay, let me go back to the text file. Save it. Now go back into Evolution. And I'll just cancel this and hit load simulation again. And there, 7 is now showing up because it's the latest saved file. And I wanted to show that anyway because it's kind of important to know whatever file you've saved most recently in that folder is the one that's going to show up by default. You can click the little arrow here and you can see other things that were created earlier. For now, I'm just going to load 7, and you can see that's all the template does. Now it looks like it's just a joint. It's not. If I grab one of these and move it, you can see there's actually 2 bones and a muscle there. That's a minimum configuration for a creature to be able to evolve in here, because it has to have a muscle in order for the neural network to function. However, again, going back into the text file, I started something else up here. Close that. Okay. Back in the text file here. If you look at this line here, what is it? The 1, 2, 3, 4, 5th line down, I have a 0 in there. That is actually telling it that I want no neural network. Normally, you would have a positive number there. 10 is the default. Sometimes it could be something like 8#8, which is adding an extra layer to it. That's of course one node on each end, and then in between you have 8 nodes on one layer and 8 nodes on another layer. And of course 10 would just be 1 node on each end, and then 10 nodes on the layer in between. For anybody who's looked at the editor for the neural network, you should know what I mean. At any rate, if I give that a positive number, then when we run this template, it won't actually run. And that's because down here, we don't have enough, way down at the bottom, we don't have enough zeros and ones. It's just a single zero for the first generation. Has to have a first generation, again, in order for this file to work. One generation has to already be saved, and this thing down here is the population. Now, if I add more rows to that, there's more population, but it'll only read the number that's listed up here in this position, the third position in the third row. That number specifies the number of members in the population. And just to keep things simple, I've got the template set to 1. Now, if you copy this template or make one like it, you can, of course, change that. Now, down here we have the section with the joints in it, these 3 joints. And I'm gonna replace that with some new joints. Now, notice the first number on each one. I've got a 1, 2, 3. Down here in the next section, 4, 5, and the section after that, 6. Okay, these 4 and 5 are in the bone section. The 6 is in the muscle section. That's the 1 muscle, the 2 bones, and the 3 joints that make up this template character. So I'm just going to go ahead and replace all that, change all that. Now, each one of those numbers has to be unique. But I could change this 4 to a 40, and then just down here, I would change this 4 also to a 40, and that would still work. So not all the numbers have to be used. These numbers in the muscle section are simply telling which bone at one end of the muscle and which bone at the other end of the muscle. In this case, line number 40 is one bone, number 5 is the other bone, and those are the numbers showing here. And if I put it back to the way it was, then of course it would be 4 and 5 instead of 40 and 5. So with that in mind, I'm going to make a few more of these. Let's just copy this. 3, 4, 5, 6, 7, and I'm going to number those. 7, 6, 5, 4, and up here, I want to set this to 0, 15. I'm gonna center this on 10. So 5 up from 10 for the center, and let's see. Going down the right hand side, 3.909 for the right, and we'll change this to 13.117. A little down from the 15. Next line down, I want to go a little farther down on the right hand side, so I'm going to go 4.875, and that's a little farther out to the right and a little farther down. Here we're going to put this at 8.888, and now we're going to go back in a little toward the center at 2.169, and down again a little more to 5.5, and we're going to make that the bottom of this object. So that's the lowest down our joints are going to get. I'm going to make one more joint at that height over here, 5.5, and I'm going to mirror the horizontal position. So put it over on the left at minus 2.169, and again moving up to 8.888, and to the left, minus 4.875. And again, moving up almost to the top, back at 13.117. And you don't need to have all this precision in there. I mean, this is a matter of choice. I'm using a little trigonometry here is all. And this one we're going to set at negative 3.909. Again, over on the left. And so there's our 7 joints. Now to put the bones in. So again, we're gonna want more than just 2 of them. I'm gonna connect these joints around in a septagon or heptagon, depending on who you ask. 3, 4, 5, 6, 7, and we'll number these 8, 9, 10, 11, 12, 13, 14. Yeah, I know I said this was going to be a quick video. I guess this isn't probably going to be most people's idea of a quick video, but for what it's showing, yeah, I think it'll still be pretty quick. Okay, so here we're just going to go basically follow the same pattern I started here: 1 to 2, 2 to 3. Going to go joint 3 to joint 4, joint 4 to joint 5, connect joint 5 to joint 6, connect joint 6 to joint 7, and connect joint 7 to joint 8. Sorry, there's no 8. 1 going back around. Okay, so yeah, 8 is a bone, not a joint. So down here in the muscles, again, we're going to make 7 of these. So 1, 2, 3, 4, 5, 6, 7. Copying that. And oh, by the way, the 0 in the last position on these joints is your 3rd dimension. It's not used in this program, but I have experimented with it a little. It doesn't change the behavior any, but you can send the joint to the background so the bones render in front of them, if you really want to do that, or bring them a little farther into the foreground. But it really behaves exactly the same as far as I can tell. And it's basically a 2D environment, but it has a 3rd dimension for positioning the joints. So here we're going to go again, number these, starting with 15, 16, 17, 18, 19, 20, and 21. Now the bones are numbered starting at 8 and ending at 14, so I'm going to go number 8 to number 9, number 9 to number 10, number 10 to number 11, number 11 to number 12, number 12 to number 13, number 13 to number 14, and the last one, number 14, not to number 15, but to number 8, going back around. Again, number 15 is a muscle, and you can't connect the bone to a muscle. You can't connect, rather, a muscle to a muscle. It has to be connected to a bone on each end. And so that's it for that object. And I'm going to save that. And again, bring up Evolution. And let's load that simulation. And there's our object that we just created. Now, it won't actually go through any generations on here. It's on generation 2, and you can see best of generation 1 up here in the corner. And I've got the timer on it set to 10 seconds. So after 10 seconds, it shows best of generation 2. It's finished generation 2, but it isn't going on to generation 3. And that's because it doesn't have any brains. Now, if I click back here I am now. Now I could edit this creature if I want. And what I'm going to do is I'm going to actually go here and save it as 7. I got to take the extra 7 off because a little glitch makes my keyboard double in this program. So there, creature 7. If I open this little menu up, there it is. Now, if I, I'll probably just go ahead and do that. I think if I want to make sure I don't lose that, in case anything goes wrong, if the program crashes or whatever, it's a good idea to close the program after saving a creature in the menu and then reopen it. So I'm just going to go ahead and do that and go back in here. And where is it? Gotta find where I put the program. Here it is. It's in this thing, in second home, downloads. There's my evolution program. So running that, and let's go with fantastic graphics. I haven't actually noticed a difference. It doesn't seem to be any faster with one or better with the other, but it has different settings. So I'll just pick that setting for now. And again, now I can select the creature here if I want. And again, if I don't have a creature selected and I load that saved simulation or saved environment, and then hit back, click back in the lower left to get out of there, that will also bring up that creature, that character. So I'm going to go ahead and select it from the menu, select 7, so that it will save as 7 if I do a little evolution. So I'm going to click evolve and just let it go through a few generations. I've got it set to 2 seconds in here per generation. Here we can give it a little bit more time than that. Just change this over here to let's say 4, and give it 4 seconds per generation, and just let it do a little bit of evolving. And you can see it starts out with something random. This is the default behavior of the program. It starts out with the population randomized, and I only have a population of 2. Let's go back and change that. I'm going to give it some more population. So remember the simulation that I loaded, it only had a population of 1. But when I hit the evolve button, that uses these settings up here. So let's change that population, say, to 11. Let's do 11, just because it's easy to type with my keyboard doubling like that. And I'll set the number of seconds per generation to, set it to 3 for starters. And I'll go ahead and click evolve. And I'm going to let this run just a little ways here, just so you can see how it works. How random this is. It's literally the brains are randomized. Now I'm going to show you those brains, what the neural network looks like in the saved file. I'm going to go ahead and click save. We're on generation 7 here. So save that and click back. I'm going to go back into my files and let's see. Here we go, back to evolution saves, and there's 7.txt. That's the creature I created, and here's 7 running generation 7. I'm going to open that file up, and here in that file, you can see over here. Here's our time of 3 seconds per generation, and our population of 11 creatures. And this 50 on the end here is your mutation rate running. That tells it which environment to load. This false here, that's telling it don't run it in batches. If that was set to true, then this number 2 would be used to tell it how many in each batch. This 10 here is the neural network. Again, that's the default. There's the creature in this area right here. And down here is 1, 2, 3, 4, 5, 6. 6 saved best of. The best creature from each of 6 generations. So it saved it as generation 7, but generation 7 has not yet been tested. Generation 6 was the last one tested. And this down here is the test of generation 6. These down here, and there should be 7, there should be, what is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There should be 11 of those. Yeah, brain froze for a moment. That's our population. And that is the population generated for generation 7. So what I'm going to do is I'm going to take that population, and I'm just going to bring it into text mechanic here. Little find and replace thing. Replace all the ones with zeros. And grab that and copy it back. And back over here to, oh, not there, to the text file. And I'm going to replace these 11 lines with the ones that are all zeros. Basically, what I'm doing is I'm zeroing out their brain. So instead of having randomized brains, now they're going to have blank brains. And I'm going to save that and go back in here, load the simulation. Now again, here it is, the last one saved, number 7, running generation 7. That's actually, it's going to show 6 generations finished, but it's going to start out with a brain dead creature. That's your brain dead creature. Notice every generation now it'll still start adding mutations to it, and so they start to change, and the better ones will tend to get selected for reproduction. But if I go up in here, you can see if I go back to number 6 here, I'm going to set that to replay a little longer. 8, 7, there's the brain dead 7, and there's generation 6. Generation 6 is from the original run, and it's just showing the best of generation 6 from that original run. Then best of 5, best of 4, best of 3, best of 2, and of course the best of generation 1 from that original run. Now if I go back and, oh, didn't mean to do that, load simulation. Before I go back, I want to save this. I'm just gonna let it run at least a generation or 2, and then just click save. Here, we'll do it on generation 9 or 10, whichever one I got there, and then click back. And again, going back to the files, there's a generation 10 running, and I'm going to rename this this generation 7 one. Just to be able to identify what I'm doing with it. Well, I should close the saved version first. Just leave it as it is for now. Go ahead and open up generation 10. And okay, here in generation 10, again, there's the saved, the 9 best of. And I'm going to grab this one here that's all zeros. Now notice the 2 below it look like they're all zeros, but if I was to scroll farther to the right, there's some ones in there somewhere, because probably there's a 50% chance of a mutation in any individual in the population. That's what the mutation rate was set at. So I'm just going to copy that with all the zeros, and the result that came up from that first one that actually was brain dead. And I'm going to just close that file. And then here in the generation 7 one, I'm going to change this so that it doesn't have all these generations, and I'm just going to replace that with just that one, and save that and close that. And I'm going to go back in here, and now I'm going to rename it. And let's rename this generation 7 to 7 running, and I'll leave the date on there, and I'll just call it brain dead because I've wiped its brain out. And then there's a starting point for running that new creature that we created, not from a random population of neural networks, but rather from a completely zeroed out population of neural networks. And again, if I go back into evolution and load the simulation, you can see that here we are. There's best of generation 1, generation 2, generation 3, and I'm going to go here and change this. Let's give it a little more time. Let's give it less. Let's give it 1 second. Let it run fast for a little while per generation, and just let it do that for a little while to get some quick mutations in here. And I'm going to go and change this, give it 8 seconds per, and then bring this back to generation 1. There's our generation 1. And okay, so that's already starting to go somewhere. Let's put this back up to 2 where it was. Let it run a little longer. Now, I want to point out something about why I'm doing this. This generally, when people run this program, they usually just use the default time of 10 seconds per generation. Now, here's the thing. This is a creature with the ability to roll. But if you leave it set to a long time for each generation, it's not likely to even learn how to roll because it's not starting out simple. It's starting out. I didn't say that right. It's starting out with no brains, so it doesn't know how to do anything, and it doesn't have all the advantage of the randomization that does actually give an advantage. But what happens is that if one of them can learn to bounce to the right consistently, just bounce, it'll outdo the ones that are rolling a little ways and then not knowing what to do from there. So if we give it a 1 second run and a 2 second run and then a 3 second run and just increase the time every so often, you can see it actually can learn to roll. And the way that happens in real life, in biology, basically, if you consider biological evolution, things that are not fit to make it to the adult stage don't make it to the adult stage. For that matter, things that aren't fit to make it as a fetus don't even make it as a fetus. There are fitness tests all along the way. And the fact that you've survived long enough to learn enough that you can understand what I'm saying, that you can watch this video and learn something, that really says something about you, that you've beat the odds. The vast majority of fertilized eggs don't make it that far. As a matter of fact, a large number of them don't even make it to the point where the person knows that they were ever pregnant. It's what's called a spontaneous abortion, and they generally happen so early that people don't even know that they've happened, because most fertilized eggs, well, I don't know if it's most, but again, a large number aren't actually viable. And here again, going to give another increase in time, and you can see it is learning to roll, but it takes a while. But it's learning to roll in spite of the fact that it started out brain dead. Now, here's the thing. if I go back to this population of 1, okay, this is a population of 11. So there are members of the population. If I go back to this population of 1, where was that? Not this one. Oh, just 7. That was a population. Was that? No, that wasn't it. I don't think I saved one of those of the population of 1 working. Well, I could make one, I suppose. Here, let's do that. Let's go back in here, and I'll just make a copy of this, and I'm just going to name this solo. Rename. Just replace the brain dead copy with solo, and save that, or rather, finish the renaming. And here, I'm going to just change this 11 of the population to a 1. Now, I could leave all these extra brains down here. They really won't hurt anything. It'll just ignore them. But I'm going to take them away and just save it without them because they're not needed. So why take up the file space? Now, going back into the evolution program, cancel, load simulation. There's solo, load that one. Now, this is a population of 1. It doesn't matter. It doesn't matter really how long I let this run. It will gain mutations. It's right now I believe it's set to 1 every 2 seconds. It's set every 3 seconds. I'm gonna go back to the 1 second like I did earlier. And if you remember right, it started gaining mutations pretty quickly that way. And there we've got 1 new generation every second, and I'm not seeing the mutations, but they should be happening. Well, maybe not. There's 1. There we go. See, but here's the thing. Every generation has that mutation now. Now there's a second mutation. Every generation has that mutation. Now the thing is, the mutation rate is set to 50%. What that means in this program is that 50% of the population will get some mutation. Specifically, the mutations that happen in those strings of binary digits. I've seen 3 to 14 at a time. I'm thinking, just because of the way programming works and the way programmers usually think, that it's probably 1 to 14, that some number of zeros or some number of digits actually get flipped from 0 to 1 or 1 to 0. Hold on. Cell phone call. Hi, I'm recording a video. All right, I'll call you back in a bit. Bye. Okay. Let's see. Where was I? So each mutation, at any rate, that happens will happen to some member of the population. Again, each member of the population gets a 50% chance of a mutation on any generation, which means all that time that it was looking like no mutations were happening on this thing, it probably was getting mutations, about 1 every other generation on the average. But not all mutations show up. They don't all cause something that you can see. And as you can see, some of the mutations that we've seen here appear to have gone away. No, they didn't go away. There's just other mutations that counteract them in one way or another. And it's extremely unlikely that the exact same mutation got unmutated. That can actually happen, but basically that means that the exact same set of digits has to be flipped. When I say digits flipped, what I mean is literally that a section of digits that have a section of ones and or zeros, all the ones get changed to zeros, all the zeros get changed to ones. And each one of the mutations, again, it's a certain number of digits is randomly picked, apparently, the number of digits. Again, I've seen it from 3 to 14. I'm guessing I'm thinking it probably can be as little as one. Actually, I think I might have even seen two, just two digits flipped. But I'm thinking it's probably from 1 to 16. Might be, it might not be, but somewhere in the genome for that member of the population, the digits get changed. Like, for example, if it was these five zeros, they would become 11111. If it was these five digits, the 11000, they would become 00111. So it's just switching everything um, from zeros to ones, or from ones to zeros. And as you can see, mutations will accumulate in this thing, and little by little, it'll get more and more mutations, but it will not learn to roll, because no matter how much or how little time I give it, because there are no other members of the population, and that's what makes the difference. People whose understanding of evolution does not include population evolution are not going to be able to understand biological evolution, because the populations are essential, just like they are in here. If you have a population of one, it's not going to basically learn to do anything particularly useful. In this case, the task is it's supposed to be trying to learn to roll to the right. But here's the thing: the way that works, the way that happens is each generation is tested to see how far did it manage to go to the right, and then each member of that population for that generation is compared. Their scores are compared. How well did they do? So they're given a fitness score, and that fitness score sort of simulates nature basically deciding what makes it and what don't. And the way that's done is those with a higher fitness score are given a higher percentage chance of getting to reproduce, getting to be involved in a reproduction. So um, basically, um, some fit member of the population will get to reproduce, and I think it just takes the most fit one and exchanges some random fraction of its genome, split somewhere, not necessarily in the middle, but split somewhere, uh, either from the beginning to that point or from that point to the end, and it'll just replace that, like, roughly half or whatever fraction of some other creature's genome with one from a more fit creature. And that's this program's idea of reproduction, if I'm summing it up correctly. That's my observation of it anyway. And so, yeah, enough of that. As you can see, you need a population for evolution to really do much of anything. I might get to it eventually. I had planned a video I was going to name When Evolution Fails, which is on that particular theme. And I was going to go into a lot more detail about this in particular. But this video isn't really about that. It's just about creating and editing creatures in a text file. And so there you are. Some creatures edited in a text file. Here, I'll show you what happens if we go all ones here. Let's go back here and replace all the zeros with ones. And let's just do that. And back in here, there's all ones. And let's change the population size to now 2 individuals, one with all zeros in its brain and one with all ones in its brain. Save that. Yeah, I probably shouldn't have saved it over as solo, but no matter, because I can change that anytime after I'm done making this video anyway. Load the simulation. And here we are with 2 members in the population now instead of just one. And now I don't know. You might have noticed there was a different member there for a while, and I think that one didn't make it. Let's have a look at the best of. Again, population of only 2. Well, it was the best of generation 2, and then best of generation 3 is going back to the one that's all or mostly zeros. So yeah, it got beat out and apparently went extinct. Again, I could go in here and make a few more of these. Let's say make 5 of each, and that'll lower the chances of extinction. And again, change the population number, in this case 10 individuals, and back, load, and that should be 10 individuals. It looks like 2, but that's only because, now it looks like 1, but that's just because they're basically all the same. And so I think all the zeros went away this time. They got beat out by the ones that were all ones. That's what appears to be the case. Now, again, mutations will happen, and eventually these things will be different from each other, but now it's starting out from all ones instead of all zeros. And if I had a large enough population to keep either one of them from going extinct for a while, eventually they would probably breed with each other, and we'd get some that are mixes of the 2, like all ones or nearly all ones at one end of the string of digits, and nearly all zeros at the other end of the string of digits. But yeah, small population. So this should give you an idea of what a difference population size makes. The Noah's Ark story of the Bible, for example, not believable for just that reason, among others. But yeah, that particular reason, that's a big one. So let's go 5 times that. Give a population of 50. A little better chance of a little more survival. And again, save, and again, back, and load, and there's our mixture. And again, it just looks like 2 of them, but that's because they're all overlapping, because they're doing exactly the same thing as each other. So I'm going to go ahead. There they didn't. So apparently mutations showed up right away, again because I've got a large population. So I'm going to go to 1 second, and in this large population, with 50% of them getting a mutation at every generation, okay, did they all go away already? I was going to say, with 50% of them getting mutation on every generation, about 25 are going to have a mutation right off the bat. But now I'm looking at that. Looks like it looks like the zeros got zeroed out. I'm going to try this one more time. I don't know if if the ones are more fit than the zeros, or what's the case. Or if there was just a lucky. No, there was a mutation there. That one went way over to the right. Oh, I see. They're squishing out. That might be why it's getting read as farther to the right, because it's squishing down, and the zeros aren't doing the squishing thing. So there we go. I think that's the solution to it right there. What's going on? Again, I go in here and let's say replace 0, 0, 0, 0, 0, 0, 0, 0 with 0, 0, 0, 0. Whoops. 1, 1, 1, 1, and replace all of that. What? Okay, something went wrong. Oh, sorry. 11111111. I forgot they're all ones in there right now. Replace that, and we'll copy that out. Go back in here, and I'm going to add a few of these. I'm going to add just a few of these at the end here. Let's go 1, 2, 3 of these. And don't need those extra carriage returns. Come on. Okay. There. All right. Uh-oh. Something went wrong, I think. 1, 2. Didn't I add 3 of them? Thought I did. Okay, so I'll add 1 more. Looks good. Okay. Get rid of that carriage return and get rid of this carriage return. So I got 3 of those. And again, back in here, I'm going to change this 00001111 to 11110000. So mirror image of it. Place. Copy. And again, add in 3 more members. It's not a lot, just something to give a little more variety to the population. And this should also demonstrate the importance of diversity, because notice we had only two models to pick from, and basically one of them just goes extinct really quickly in this particular case. So here we're going to go to 56 because I added 6 extra characters, and save that. Extra creatures. And again, back out of here. And load simulation. And there we are now with 4 different kinds instead of just 2 different kinds. And again, let's just give them a single second for a while so we can rack up some mutations, and hopefully they won't all go extinct. Maybe if I gave them more time, I wouldn't be making them all go extinct so quickly. I seem to have extincted them already that way. That might be exactly why, because that one squishes out in that first second. I think I might have found the problem. Let's do that. Load simulation. Load. Instead of giving it less time, let's give it more time. Now, it's taking more than 3 seconds, but that's because there's a lot of members in the population. So I'm going to go bring this down to batches of 28, and that should make 2 batches out of this, so they can run a little more smoothly. Now, again, I could experiment with this all day long. You can do your own experimenting. It looks like, again, these ones just wipe the other ones out. So at least initially, they're much more extinct. They're much more fit for that first second. Again, by the measurement this program is using, because the program is measuring how far they made it to the right, and squishing themselves out makes it look like they've made it to the right. If I go back to generation 1, you can see this one didn't go anywhere, 0.0 meters from the start to the right. Number 2, 0.3. Number 3, 0.3. Number 4, 0.4. Number 5, 0.4. Number 6, 0.4. Number 7, 0.3. So they're not really making a heck of a lot of progress. There's 0.4 again. 0.4, and number 9 isn't quite ready yet. Or, yeah. What is it? Oh, I see. Generation 11 batch. It's on 10. Generation 11. Oh, it's still doing the batches. Two batches for each. So there's 0.4 on this one and 0.4 on that one. And again, it might take a long time before it gets to 0.5 meters or 0.6 meters. But eventually the mutations will come along that will do that. There's enough members in the population that'll happen. But this squishing out thing apparently just makes that big of a difference at the start, that none of those other ones got reproduced at all. So yeah. Any rate, that's it for this video. Thanks for watching. I hope you've enjoyed it, and I hope my statement that it was going to be a short video wasn't too misleading, because it certainly wasn't intended to be. Take care.